So let's move on to compressing data. All right. Storage is really cheap nowadays compared to what it used to be. Storage is so much cheaper than it used to be. It becomes increasingly cheaper and cheaper. Used to we all had the hard drives that were measured in RPMs, right? Revolutions per minute, because it's an actual physical spinning disk inside there, and they were initially I don't know, like used to, you'd have like I think the problem that the computer that I bought just I don't know, not too many years ago, came with a terabyte. What's the old legacy drives that I'm trying to think of? The old hard drives. The new thing is SSDs, right? Like the SATA hard drives, which the SATA had to do with the way that it connected to the motherboard, right? It had to do with that connector there. But the idea was those old spinning disks, and I feel like there's another name that I'm not remembering there, but it's measured in RPM. So then we kind of moved on to the solid state drive, so there's no moving parts with that, so it was much faster. And when those first came out, they were really expensive. But now, I mean, you can get a terabyte hard drive, SSD drive for, I don't know, I think I saw one for like $160 or something like that. They may be cheaper than that. I don't know. But they just continue to come down. All the prices for the storage continues to come down. But why do we still have to keep having bigger storage devices? Because even though the price goes down, what's happening?
Files are getting bigger.
Files are getting bigger, right? Everything's like used to it was just, we had 1080p video, and that was yes.
You used to like load video games in the consoles and they'd be able to run instantly. Now you have to actually download everything in hundreds of gigabytes and such on.
Right, yeah, I mean, it's like all like for the games, the 3D games, they just get bigger and bigger and bigger in size. Video, like I said, used to it was, we had DVDs, and they were, I can't remember what DVD drives, they hold like, I want to say like it's around 700 megabytes or something like that of information. And then Blu-rays came out, which were like 4.6, or maybe I'm more 4.7 gigabytes, maybe I'm getting confused, maybe 4.6. Yeah, CDs I think were 700. And then DVDs, maybe they were 4.6, I don't know, but it kept getting bigger and bigger, right? We had 1080p video, now you got 4K video, so even though storage gets cheaper, the file sizes get larger. And so and for that reason, we have to discuss the topic of compressing data. And so that's what this chapter is all about, right? Compressing data. It's Howard, right?
Yeah. Wait, me?
No.
Yeah, it's me.
You're Howard.
He's Hudson.
You're Hudson, yeah. You guys shouldn't sit next to one another with names that start with H, okay? Just try not to let that happen. What's that?
We're running protection chain again, so you got to take that one.
Okay. All right, so we got to discuss compression, not only because of the files stored on our computer, but what are we doing with all of these files? In addition to storing them locally, we're also transmitting them across the internet, right? And there's there's this idea of bandwidth, which means basically there's a pipe that's a certain size as we're transmitting this data. And there's only so much data that can fit through that pipe. That's kind of the way to think about that. And so when you're transmitting these huge files, particularly like video files that are so large, you have to be able to compress this data because the bandwidth just can't keep up with the amount of data that you're trying to transfer. There would be no way that most of us would be able to watch 4K video when we're streaming it, down to our homes, unless there was some compression going on there, because the raw image files are just too large, the raw video files. So when you're deciding how to compress your data, it's kind of a decision between two different, there's two trade-offs there, two factors that sort of determine how you do it. One is size. So we're trying to find a balance between the size and, number two, the quality. So how do I want to write that? So let's see, as compressed data, trying to, let's see, as compressed data, consider two main factors. The size of that data and then the quality of it. So you're trying to find what's the what's the smallest file size I can get, right, but still deal with a quality that's acceptable. So if I'm watching the video, right, there's a certain clarity that I'm going to be satisfied with, and depending on whether I want super high quality or maybe I can just take it down to about 80% of what it was before, which it still looks okay. I can't tell a noticeable difference, but it made a big difference in the file size. So there's a trade-off between those two. That's supposed to say quality, but my U looks sort of weird there. So make sure you know that, right? Those are the two things that matter. For those of you that don't like to take notes in class, make sure that when I write something on the board that you know that, right? That you've committed that to memory, because those are the types of things that show up again on tests and on quizzes. But there's a trade-off between those two, right? If quality is preeminent in your decision, then you're probably not going to be able to save much space. You just have to be okay with that. You're going to have to buy more drives, right? Buy bigger storage. But if you just want a video to look okay on a laptop, that's a much smaller form factor, a much smaller screen size, and we can get away with some smaller video if that's kind of the form factor that we're viewing that on, right? If I'm viewing something on my phone and I know it's going to be primarily viewed on my phone, I don't necessarily care as much about the quality of the video as I do if I've got it on some new, 72-inch 4K television. Is that even a size? I don't know. I've seen 65, so there's probably, I don't know what the jump is, but they're getting really large, right? And for these high quality ones, they look great, so you're going to have a high quality video for it to look great on there. If we say a file is uncompressed, what do we mean by that? Aiden.
It's just raw bits. It's in no way changed.
It hasn't been changed at all. All of the original data is exactly in the same, all that information in the original one is still there. All information from original file is intact, right? Same format. Same number of bits. So down to the bit level, it's all the same. So it's the same size, right? And also same format too, because there are changes that are going to take place to that data if we convert it to a different format. Now it is important that we understand anytime you go from an analog signal to a digital signal, that some of the data has been lost. Just going from, when you think about, if anybody's seen a picture that kind of looks like this, like here's a wave, there's the analog sound wave, and then when you look at like a digital representation of it, it may look something like this, where you have all these like steps. I'm kind of getting confused as I'm doing these, but you got all these little steps, kind of jagged version of it. Sometimes you may see representations of it where these are sort of like, it looks kind of like a bar chart where you got these lines beneath this here. But this is supposed to be like the digital representation of this analog wave, right? And so because we're converting it to a digital format, we're going to lose some information. It's not going to be exactly the same. That's why some people still listen to record players instead of CDs, right? Because they're like, I want to hear the pure sound. I want to hear the true audio wave, the true analog signal. Even though there's some static and stuff in there, I'm hearing the pure signal versus this thing that a computer has taken and digitized. They recognize that you lose some of that information. And so what they call the true audiophiles, as they call themselves, when I say audiophiles, it's spelled like this, right? But they're like, no, we can tell a difference, man. When you convert it to the digital one, we hear some stuff missing there. So they like to listen to the analog version on a device, like a record player, or a reel-to-reel tape or something like that. So we're going to lose some data just by converting it to digital. But in order to be able to work with these files, because they can get really large, then we also start talking about compressing that data. And when we do that, we choose a particular codec. You guys ever heard that term, codec? You familiar with that? You ever tried to play a video file on your computer and it's like you don't have the correct codec? You know, you need to download a particular codec in order to watch this file. And so a codec, the definition for that, this is a computer program that encodes and decodes data. And so you can kind of remember that if you think about the COD portion of encode and the DE portion, I'm sorry, not the DE, of DEC, I'm sorry, the CO portion of encodes and the DEC portion of decodes, and it makes the word codec. So we choose a codec in order to save space. It encodes the original file, and you have to have that same codec in order to decode the file so that you can watch it or listen to it on whatever device that you're watching it or listening to it on. But there are kind of two sort of techniques when you're converting, when you're compressing this data. And there's compression that we call lossy. What does that mean, Isaiah? Do you know?
No.
When we say it's lossy, what does it sound like it means?
Loss.
Loss. There's loss, right? The idea is that when we're compressing the data, we lost some data in the process. All right. So compression, which is lossy, means that you lose data when compressing. In other words, some information got thrown away. There's no way for us to get back to the original. It's gone for good. You know, we can't even recreate it in from our compressed file. So that's lossy data. Now there's a branch of physics that's called psychophysics, and I've always said, wouldn't that be a cool job to have, to be able to tell people I'm a psychophysician? I wonder how people would respond. You know, what do you do for a living? I'm a psychophysician, and just kind of stare at it and see what happens. You know, be kind of strange. Psychophysics. I don't know. I just thought you guys didn't think that was as funny as I did. I thought it was hilarious. Psychophysics. So that's a branch of psychology, and what psychophysics has to deal with is it studies the ability of the human eye, or ear to detect the loss of certain data. So that's been really helpful when we've talked about, I'll let you guys finish writing that down. Kind of running against the clock here, so sorry if I'm moving a little fast. Just want to get us through this section here. So when we talk about lossy forms of compressions, the study that psychophysicians have done has been really helpful because in this branch of psychology, they've been able to tell us that, hey, the human brain doesn't even isn't able to see these colors, right? Or isn't able to distinguish between this many shades of this color. They may say, you know, as far as shades of gray go, the human eye can only distinguish between however many. We've looked at, he tells us later in the chapter, I don't remember what the number is, but something like 22 or 23 shades of gray. And so if we've got a picture that's got more than that number of shades of gray in it, then these studies have told us that we can throw away those extra shades and just make them all the same color, and the human eye doesn't even recognize it, right? So that's some way that we can save data, compress data down, is by getting rid of information that humans can't see or that humans can't hear. So with the audio, for example, there's a sub-branch called psychoacoustics. Sub-branch of this. Psychoacoustics. And since it's psychoacoustics, what does that seem like it has to do with? Hearing, right? So that's specifically the hearing portion. So they focus on that. Right? What the ear can perceive. And they've said, hey, there are certain frequencies that the human ear just can't perceive. So what's the point in keeping that information on our recording, right? We just throw it away when we compress it down. The human ear can't distinguish it anyway. So there's some compression that is lossy, but there's also lossless compression. Anybody want to take a stab at what that is?
It doesn't lose anything.
It doesn't lose anything. Can you elaborate more on that, Josh?
Um,
Oh, we didn't expect that, did he?
So maybe you can, I guess,
We are compressing it.
yeah, lose like data, but it can be restored.
It can be restored. Good job. Good job. So that's the key, right? We're still compressing it. So in order to compress it, we had to make it smaller so it's not identical to the original file. But no data is lost. No data lost. Can restore to original form. So no data lost, though smaller size. So still compression. And there are some things, like with audio, I can throw away some frequencies that the human ear can't hear anyway, so what does it matter if I get them back? But what if we're talking about text? Let's say I'm compressing email, right? Because there's so much email that floats across the internet. I mean, one email may be really small file size, but when you think about billions and billions and billions of emails being sent out every day, we've got to compress that data because it's just too much data. The internet would come to a screeching halt, right? And so we have to compress it, but we have to compress it in a way so that we don't lose any of the original information, so that when you view my email on the other side of the world, you know, there's not words letters that are missing or anything like that, right? We have to be able to have the original. And so that's where these lossless compression techniques come into play, which is what we're going to spend basically the next lecture focusing on. But let me just say this. When you talk about lossless compression, one final point is that in addition to the data itself, you have to store what we refer to as metadata. So compressed files often contain metadata. And does anybody give me like a quick definition of metadata? Do you know what that is when we use that term? Yes.
Is it like a...
Wait a minute. Braden, are you on the board? Let's give Braden a shot here because he's not on there yet. Braden, take a stab at it.
Is it like the most important data?
The most important data. What would you say to that, Aiden?
It's kind of like the info needed to bring back the other data, right? It's kind of
Yeah, it's most important in the sense that maybe you don't know, you have to have this data to understand the data that's in the file. So it is important in that sense, so I would agree with that. But more specifically, kind of more along the lines of what Aiden's saying here, it's data about the data. It tells you about the data that's there, right? So that's a definition that you'll sometimes see. It's data about data. It's like information in the file that tells you about the information that's in the file, if that makes sense. And so it's data about the data, or data that may also see it written as data that describes data. And so it may be stuff like, may include info like author, title, location, right? It's kind of like the stuff, if you look at your phone, if you look at the details on a picture that you took on your phone, and you'll see maybe who took it, or maybe the date or the location, and that type of stuff, that's metadata, right? It's not really the image, it's not the main data that we're concerned about, but it's important information about the file. And so this information is usually stored at the beginning of the file. And so metadata really applies more to just compressed files, but it's going to be crucial with compressed files because a lot of times we're storing information at the header of the file that tells us how to uncompress it if it's like this lossless format, how you can uncompress it and get it back into its original state. All right.